today's lecture of the course Mathematical Aspects of Biomedical Electronic System Design. We will continue our discussion on probability and random variables. In today's lecture, we will cover expectation and higher moments, variance and standard deviation. We will also see probability and moment generating functions. So let us start today's lecture. We will begin with expectation of random variables. Expectation is a measure of center or average value of a random variable. We will consider the cases of discrete and continuous random variables separately. So let us begin with discrete random variables. Suppose x is a discrete random variable with cumulative distribution function f. So f has jumps and flat portions. Suppose f has jumps at xi I greater than or equal to 1. This means that the random variable x has point masses pi at this point xi. Pi has probability of x taking values xi. So point masses pi, which are probability of x being equal to xi, and these are given by fxi minus fxi minus 1 for all I greater than or equal to 1. In fact, for this definition we can assume that fx0 is 0. Then expectation is given by the following formula. Expectation denoted as E of x is summation I greater than or equal to 1 pi times xi. If x takes values in the set of non-negative integers, then we have an alternate formula of expectation. We will see that below. So if x takes values in the set 0, 1, 2, dot, 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 then as per the previous formula, expectation would be given by I greater than or equal to 1 I times pi. As I said, we also have an alternate formula that says that expectation will be equal to I greater than or equal to 0, 1 minus fi. Okay. Notice that this is equal to sum I greater than or equal to 0, probability that x greater than I, which in turn is equal to summation over I greater than or equal to 1, probability x greater than or equal to y. So we have this alternate formula for expectation. We will see a few examples very soon, but for now let us turn to continuous random variables. Suppose x is a continuous random variable with cumulative distribution function CDF f and probability density function small f, then expectation of x denoted as E of x is given by minus infinity to infinity x fx dx. If x is a non-negative random variable, then as in discrete case, we also have an alternate expression of expectation which is given as follows. So if x is a non-negative random variable, then expected value of x is also given by 0 to infinity 1 minus fx dx. Let us now see a few examples. Let's consider a simple example where a die is tossed. And we define a random variable x as defined as x omega is CL of omega by 2. We have seen this example quite a few times earlier also. Then clearly x takes values 1, 2 and 3. Moreover, probability of x taking value I, that is pi, probability of x taking value I, this is 1 by 3 for all I, that is I equal to 1, 2, 3. So expected value of x would be given by 1 by 3 into 1 plus 1 by 3 into 2 plus 1 by 3 into 3, which is, it turns out to be 2. Let's consider another example. Now assume that x is a continuous random variable with density, that is probability density function, f given as fx equal to e raised to minus x if x is greater than or equal to 0 and 0 otherwise. So this density looks as follows. Then expectation of x can be computed using the formula suggested above, that is 0 to infinity x e raised to minus x dx. This is minus e raised to minus x e raised to minus x 0 infinity, which is 1. Observe that in this case we can compute the CDF of x as follows. Fx will be, so CDF fx will be 0 to x e raised to minus z dz for x greater than or equal to 0, and it will be 0 for x less than 0. So this turns out to be equal to 1 minus e raised to minus x for x greater than or equal to 0 and 0 for x less than 0. Now we could use even the alternate formula given above to compute the expectation, that is expectation of x will be 0 to infinity 1 minus fx. So 1 minus fx dx, which will be 0 to infinity e raised to minus x dx, and this we can see that equal to 1. Okay. Let's now see another example. Say that x is a discrete random variable and x takes values in z plus plus. This fact that x takes values in z plus plus is often written in short simply as x belongs to z plus plus. Okay, and probability mass function of x is given as follows. Pk, that is probability that x is equal to k, is 6 by pi square k square. This is for all k greater than or equal to 1. It can be checked that summation of pk, k greater than or equal to 1, is 1. So this p is a valid probability mass function. Now the expectation of x can be computed using the formula above, that is Expectation of x equals k equals to 1 to infinity k times pk, which is 6 by pi square k square. So this is k equals to 1 to infinity. 6 by pi square is anyway constant, so we will take it out. So k by k square, that gives 1 by k, but we know that this summation is infinity. So expectation turns out to be infinity. This tells that expectation of a random variable can be infinity. Let's see one more example. This time we will consider a continuous random variable. Continuous random variable with density, that is PDF f given at fx equal to 2 by pi alpha by alpha square plus x square for all x in R plus, that is for all non-negative x. Fx is 0 for all x less than 0. So x is a non-negative random variable. In this case, the CDF of x, say f, can be computed as follows. F of x is clearly 0 for all x less than 0 because x is a non-negative random variable. But for all non-negative values of x, fx will be given by 0 to x small fz dz. Now 2 by pi is a constant, even alpha is a constant, so we will take that out. What we'll have is 0 to x 1 over alpha square plus z square dz. On simplifying, this turns out to be equal to 2 by pi tan inverse x by alpha for all x in R plus. Now we can compute the expectation of x using one of the two formulae given above. So let us use, for instance, the formula that uses density. So 0 to infinity x fx dx. So this is 2 over pi 0 to infinity alpha x over alpha square plus x square dx. This is alpha over 2 pi 0 to infinity x by alpha square plus x square dx, and this on evaluation turns out to be infinity. So again we see that expectation of a continuous random variable can be finite or infinite. There are also random variables whose expectations are not defined. However, we will not be interested in those random variables. We'll restrict to random variables whose expectation is defined. It could be finite or infinite. Having seen the expectation of a random variable, we will now turn to functions of random variables and we'll see how their expectations could be computed. So, next we see functions of random variables. Suppose x is a random variable and G is a mapping from R to R. Then Gx may or may not be a random variable. However, we are interested in scenarios where Gx is a random variable, and in those scenarios we are interested in expectation of Gx. Assume Gx is a random variable. Question is, what is expectation of Gx? We will again consider the two cases of x being discrete and continuous separately. So we will first consider the scenario where x is discrete random variable. Suppose x has point masses pi I greater than or equal to 1 at points xi I greater than or equal to 1. In this case, expectation of gx can be computed as follows. Expectation of gx is summation I greater than or equal to 1 pi g of small xi. On the other hand, if x is a continuous random variable, say x has density function or PDF f, then expected value of gx is computed using the formula minus infinity to infinity g of small x f of small x dx. Okay, let's see a few examples. First example is where we assume x to be a discrete random variable. So x is a discrete random variable Suppose the probability mass function of x is as follows. So px, pmf, p is as follows. P of small x is 0.2 if x is 0, 0.5 if x is 1, and 0.3 if x is 2. This means that x takes values 0, 1, 2 with probability 0.2, 0.5, 0.3, or x has point masses 0.5, 0.2, 0.5 and 0.3 at 0, 1 and 2 respectively. Consider a function of this random variable capital X, gx to be x square. In this case, expected value of x square can be computed using the formula given above. So expected value of x square will be summation I equals to 1 to 3 xi square pi, which will be 0.2 into 0 square plus 0.5 into 1 square plus 0.3 into 2 square, and this turns out to be 1.7. Let's consider another example, this time of a continuous random variable. So x is a continuous random variable with density f given as follows. F of small x is 1 for all x in 0, 1, and it's 0 for all x not in 0, 1. So recall that we refer to this random variable as uniformly distributed over 0, 1. This is how the density looks like. Now consider a function gx which is equal to x cube. Then expected value of x cube can be computed using the formula given above, that suggests that expected value of x cube will be x cube fx dx integrated from 0 to 1, because that is the interval over which fx is positive, and in fact it is 1 over this interval. So this becomes 0 to 1 x cube dx, which is 1 by 4. Let us now see a few properties of expectation. Suppose x1, x2, dot 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 xn are random variables defined on the same probability space, say omega f p, then their summation xi equal to 1 to n, this is also a random variable, and expectation of this new random variable is sum of expectations of individual random variables. This property is called linearity of expectation. This is quite useful property, and in fact we will see one of its uses very soon. Similarly, if alpha beta are constant, say they are real numbers, then alpha x plus beta is also a random variable if x is a random variable. Expectation of this new random variable is alpha times expectation of x plus beta. Let's see an example. Suppose a die is rolled thrice. Die is tossed thrice. Okay. Let xi be the outcome of the ith roll. Outcome of the ith roll, ith toss, where I is varying from 1 to 3. Also, let x be summation of these three random variables, I equals to 1 to 3. Then expected value of x from linearity of expectation will be summation I equals to 1 to 3 expected value of xi, and each of these we can compute. So for instance, expected value of xi would be j equals to 1 to 6 j times probability of xi being j, which is 1 by 6, and this will be equal to 7 by 2. So expected value of x will be 7 by 2 plus 7 by 2 plus 7 by 2, that is 3 times 7 by 2, which is 21 by 2. After expectation, we now turn our attention to the so-called higher moments of random variables. Higher moments. Okay. For a random variable, x and a non-negative integer, rather a positive integer n, the quantity expectation of x raised to n, this quantity is called the nth order moment of x, or sometimes simply nth moment of x is called nth order moment of x. A related concept is that of central moment. The quantity expected value of x minus expected value of x whole raised to n, this is called nth order central moment of x, or sometimes simply nth central moment of x. Nth order central moment of x. Of special interest is the scenario when n is 2. Special case is when n is 2. In this case, the quantity expected value of x square is clearly the second order moment, and expected value of x minus expected value of x whole square, this is second order central moment, and this second order central moment of x is what is widely known as variance of x. Widely referred to as variance of x. In fact, it's denoted by var x. So var x is expected value of x minus ex whole square, and it turns out to be equal to expected value of x square, that is second order moment, minus expected value of x whole square. Notice that this is expectation. So variance is nothing but second order moment minus square of expectation. Square root of variance is known as standard deviation of the random variable. So let's see standard deviation. Standard deviation of a random variable is square root of variance. It's often denoted as STD-DEV. So STD-DEV of x is square root of variance. Now we can use any of the above two formula for variance. So for instance, it can be written as expected value of x square, expected value of x whole square, square root of this whole thing. So this is standard deviation. So we have thus defined variance and standard deviation of random variables. Let us see an example. Assume a random variable x, which is discrete random variable. So consider a discrete random variable x with PMF P given as P x equal to n is c by n cube, n greater than or equal to 1. So c here is a constant. Random variable x is thus taking all positive integer values, and these are the point masses at those points. Okay, and notice that for p to be a valid probability mass function, we require that summation n equals to 1 to infinity p x equal to n b equal to 1. That is, we require that c times n equal to 1 to infinity 1 over n cube b equal to 1. So c has to be set to be equal to n 1 over n equal to 1 to infinity 1 over n cube. Right? So c is this constant. For this region, the c is also termed as normalizing constant. Okay, so let us see what will be the expectation and variance of this random variable. The expectation of x can be computed using the formula given above. So it will be n equal to 1 to infinity n times c by n cube. C is a constant, so this becomes n equals to 1 to infinity 1 over n square, and we know that this summation is equal to 6 by pi square. So the expectation turns out to be equal to 6c by pi square. Now let us look at the second moment, expected value of x square. This, from the formula of expectation of functions of random variables, can be written as n equal to 1 to infinity n square times c by n cube. So c times n equals to 1 to infinity 1 by n, and we know that this summation is infinity. So the second order moment of x in this case is infinity. Okay. Now let us turn to variance of x. As we have seen above, it is difference of second order moment and square of expectation, but the second order moment is infinity. Second term is finite, but the first is infinite, so this is also infinite. Clearly, in this case, the standard deviation of x will also be infinite. Next, let us see the notion of probability generating functions. These are called PGFs in short. Probability generating functions are defined for discrete random variables that take non-negative integer values. Consider a discrete random variable x taking values in the set 0, 1, 2, 3 dot dot dot, that is in the set z plus. Suppose the PMF of x is p. X has PMF p, that is probability that x will take value k is pk for all k greater than or equal to 0. Then the probability generating function of x, PGF, is a function g from R to R defined as follows. So g of z is expectation of z raised to x, that is, it is k equals to 0 to infinity pk z or k, and this is for all z in R. Okay. So this is how we define probability generating function. Let's see a couple of examples. First example is, suppose x is a discrete random variable and it takes values 0 or 1. Moreover, probability of x equal to 1, that is p1, is say p. Clearly p0 in this case will be 1 minus p. Then pgf of x, g is given by the expression 1 minus p plus p times z. This is for all z in R. Let's consider another example. Suppose again x is a discrete random variable, but now it's taking values in z plus. Dot dot dot. Right? Suppose x has PMF P, that is given as follows, given as pk is e raised to minus lambda, lambda raised to k divided by factorial k for all k greater than or equal to 0 for some lambda that is positive. Now we can use the formula above to compute the probability generating function of x, that is g as gz equal to k equals to 0 to infinity e raised to minus lambda, lambda raised to k divided by factorial k. This is pk times z raised to k. This turns out to be equal to e raised to lambda z minus 1. Now let's see a few properties of probability generating functions. The first property is, the PMF of a random variable can be recovered from its probability generating function. PMF of x can be recovered from its PGF gz. In particular, pk turns out to be equal to, that is px equal to k, turns out to be equal to 1 over factorial k, kth derivative of g evaluated at z equals to 0. This is true for all k greater than or equal to 1. In fact, p0 can be easily seen to be equal to g0. So this is how we can recover the whole PMF from the PGF of the random variable. The second property says that probability generating functions uniquely determine their distributions. Probability generating functions uniquely determine distributions. What this means is that if x and y are two discrete random variables taking values in z plus, suppose their PMFs are px and py, their PGFs are gx and gy. If gx and gy are same, that is if gxz is same as gyz for all z in R, then their PMFs will also be same. That is pxk will be same as pyk for all k greater than or equal to 0. The third property says that g of 1 equals summation k greater than or equal to 0, that is k equals to 0 to infinity pk, and so it equals 1. Given that x is a proper random variable, that is an assumption that we are making all through. The fourth property tells that expectation can be computed from PGF of the random variable. In particular, expectation of random variable x turns out to be equal to derivative of PGF evaluated at z equal to 1. In fact, moments of all orders of x can be recovered from the PGF, can be computed from the PGF. We will not look at moments of all orders, but we will be interested in second moment and variance. It turns out that second moment of x, that is expected value of x square, equals second derivative of PGF evaluated at z equal to 1 plus derivative of PGF evaluated at z equal to 1. Clearly, we can write even variance of x using the above two expressions in terms of PGF of x. Particular variance of x is given by this expression at z equal to 1 plus derivative at z equal to 1 minus derivative at z equal to 1 whole square. Notice that the last term is square of the expectation. Let us now illustrate this relations with a couple of examples. In fact, we will revisit the two examples that we saw above. Examples. First example above. Recall that in the first example above, the PGF was 1 minus P plus Pz for all z in R. So, mean of the random variable x here can be computed as derivative of PGF, that is P evaluated at z equal to 1. So, this is simply P. The second derivative of Gz at z equal to 1 plus its first derivative at z equal to 1. The second derivative of Gz is 0. First derivative computed at z equal to 1 is P. So that is how we get the second moment, and the variance of x can now be computed at P minus P square, that is P times 1 minus P. Let's now see the second example above. Recall that in this example, the PGF was e raised to lambda z minus 1. So expectation of the random variable x can be computed as derivative of Gz evaluated at z equal to 1. Its derivative is lambda times e raised to lambda z minus 1. When evaluated at 1, we simply get lambda. Second moment of the random variable x will be the second derivative, say lambda square e raised to lambda z minus 1 evaluated at z equal to 1 plus first derivative evaluated at z equal to 1, which lambda e raised to lambda z minus 1 evaluated at z equal to 1. So this turns out to be lambda square plus lambda. From the above two, we can see that variance of x will be lambda square plus lambda minus lambda square. So it will simply be lambda. Finally, let us see the notion of moment generating functions. In short, these are called MGFs. The moment generating function of a random variable x is a mapping M from R to R defined by mt equals to expected value of e raised to xt for all t in R. We assume that this expectation exists. Note that e raised to tx can be expanded as n equals to 0 to infinity t raised to n x raised to n divided by factorial n. So mt can be computed using linearity of expectation as n equals to 0 to infinity t raised to n expected value of x raised to n divided by factorial n. Let's see a few examples. The first example, let us again consider x to be random variable, discrete random variable that takes value 0 and 1. P1, that is probability that x equal to 1 is P, and P0 is 1 minus P. In this case, following the above definition, we can write MGF MT to be equal to P, actually 1 minus P plus P e raised to T. This is for all T in R. Let's see another example. Now we assume that x is discrete and it has PMF. P as follows: Pk is e raised to minus lambda, lambda raised to k divided by factorial k for all k greater than or equal to 0. In this case, mt can be seen to be equal to k equals to 0 to infinity e raised to minus lambda, lambda raised to k factorial k times e raised to kt, which is k equals to 0 to infinity e raised to minus lambda, lambda times e raised to t whole raised to k divided by factorial k, and this can be seen to be equal to exponential of lambda e raised to t minus 1. Let's see one more example, and this time we take x to be a continuous random variable and probability density function of x is fx equal to lambda e raised to minus lambda x for x greater than or equal to 0 and 0 for x less than 0. Now for this random variable, mt can be written as 0 to infinity lambda e raised to minus lambda x e raised to tx dx, and it can be seen that this function is only defined when t is less than lambda, in which case the function turns out to be equal to lambda divided by lambda minus t. So here t is less than lambda. MGF is defined only for t less than lambda. Let us now see a few properties of moment generating functions. The first property is, like probability generating functions, moment generating functions also uniquely determine the distributions. Moment generating functions uniquely determine distributions. That is, if we have two random variables x and y, two random variables, and say these random variables have cumulative distribution functions fx and fy, and moment generating functions mx and my, if mx is equal to my, that is, if mxt is equal to myt for all t in R, then fx is also equal to fy, that is, fx x is equal to fyx for all x in R. Okay, so the distributions of the two random variables are also same. The second property says that m0, which is expectation of e raised to 0 times x, that is expectation of 1, is simply 1. The third property says that expectation of the random variable can be recovered from the moment generating function. In particular, the expected value of x turns out to be dmt over dt, that is derivative of moment generating function evaluated at t equals to 0. In fact, as in the case of probability generating functions, moments of all orders can also be recovered from moment generating functions. In particular, for all n greater than or equal to 1, the nth order moment of random variable x turns out to be equal to nth derivative of moment generating function evaluated at t equals to 0. So clearly we can compute second order moment, variance, etc. from the moment generating function. In particular, variance of x would be d square mt over dt square at t equals to 0 minus dmt over dt at t equals to 0 whole square. Let us see a few examples to illustrate these relations. We will revisit the examples that we have seen above. So first example above. Recall that in the first example above, the moment generating function was 1 minus p plus p e raised to t. So the expectation of the random variable x ex can be obtained as derivative of the moment generating function, that is p e raised to t evaluated as t equals to 0. So this is p. The second moment can be obtained as the second derivative of moment generating function, that is again p e raised to lambda t evaluated at t equals to 0. So this is also p, and so as before, variance is p times 1 minus p. Let us now look at one more example, which is actually the third example seen above. Third example above. Recall that in the third example above, the moment generating function mt was lambda over lambda minus t for all t less than lambda. So expectation of x, the random variable x, can be computed by differentiating mt and evaluating the derivative at t equals to 0. So the derivative of mt in this case is lambda divided by lambda minus t whole square, and when evaluated at t equals to 0, it gives 1 over lambda. Next, the second moment of the random variable ex square can be computed as twice differentiating mt and evaluating the expression at t equals to 0. Twice differentiation of mt gives 2 lambda by lambda minus t whole cube, and when we evaluate it at t equals to 0, we get 2 by lambda square. So variance of x can be computed as expected value of x square, that is 2 over lambda square, minus square of the expectations 1 by lambda whole square, and so we see that the variance is 1 over lambda square. From variance we can also compute the standard deviation of x. This is simply 1 over lambda. So this was about moment generating functions. This brings us to the end of this lecture. Thank you.